welcome to our bilingual course. Before we start our lesson today, and I want to review some topic. The topic we have learned before is talking about a magnetic effect of electric current. So you can ask yourself, who is he and what is this effect? Okay, I think everybody is familiar with this effect, so I need to emphasize who is he. And he is Danish physicist, and Ørsted, he did demonstrate the experiment in 1820, and it talk about electric current can produce magnetic field around. Okay, so it is good for a magnet was produced from electricity, but it will be better if we can create electric current from the magnets. Because if we can do that, we can produce electric current, and now we can store power, and we can power up our entire city. So is it possible? I think the answer is yes, definitely. 也就是说，如果我们今天可以把这个电磁场就是磁场它产生这个电流的话呢，那我们就是可以非常的方便嘛，因为毕竟在我们日常生活中，我们有非常多的东西是要运用到这个电力的。So today we are going to talk about electromagnetic induction. Okay, so we will do some abbreviation. So we will call it EM induction. So this induction was found by Michael Faraday and in 1831. So I will demonstrate some experiment for you, and you can see in the middle it is a solenoid, and left hand side is this one is a galvanometer. Okay, it's a galvanometer. We have a thin needle in the center here. So we will see when I insert the magnet or make the magnet leave, and we can see the number shows in this galvanometer. Okay, I think it's obvious when we insert the magnets and the galvanometer detect the current, and when the magnet leaves, and it also detect the current. So we will use some question to make you understand it. So I need to ask you again, when does the galvanometer detect the current? I think the answer is obvious when the magnet is close to the solenoid, or when it leaves and we can detect the current. So here is some animation. So when the magnet is close to coil to the left, and we can see obviously there is a current. And the other case is when magnet leaves. When it leaves, and it also shows the direction of current. Okay, so we can see no matter the magnet is close to leaving, and it can generate the current, and the galvanometer detect it. But we can understand the direction is different here. Okay, this is left word and this is a right word. So let's see again. The current produced because of the relative motion between the coil and magnets. Okay, so what is changing in the coil? If we already learned before, like magnets, 就是我们都知道磁铁它有两极嘛，有 N 极跟 S 极嘛。那在 N 极跟 S 极的时候呢，它会产生什么东西呢？那想必大家都知道，一定是磁场。那磁场就是在这个磁铁在靠近或者是远离这个线圈的时候，那到底会有发生什么改变？这样子。So I think the answer is obvious because the magnetic effect lines are changing inside the coil, or you can just say magnetic field. Okay, so we can understand. So produce the current due to a changing magnetic field inside. Okay. So now, upon above demonstration, so I want to ask you which following magnetic field can generate current. Okay, one is a stationary magnetic field, and second is a changing magnetic field. So you can answer it yourself, and you can see the answer after you think about that. 好，那这个应该比较简单，我相信大家应该都是可以答对的了哈。The answer is changing magnetic field because when we close to or we are living, the magnets are living, you can generate electric current. So let's sum it up shortly. So what is EM induction? When you change the magnetic field through a coil, it will induce a current immediately. And in order to distinguish the current is not from the battery, so we will call it induced current. 就是那个时代，我记得好像都是用伏打电子嘛，用伏打电子来产生一些电力嘛，所以我们要做一下这个区别，这样子。Okay, if there is no question, let's continue. So here comes another question. How can we know the direction of induced current? So in the magnetic effects of electric current, when Ørsted found this phenomenon, and Ampere and shows a method to decide the direction of the magnetic field. We call it the right-hand rule. So now, how can we know the direction? I think some scientists will find out. And this scientist is a Russian scientist, Lenz. So Lenz is talking about, is saying the induced current will create a magnetic field. And this magnetic field will always opposes the change in the initial magnetic field. Okay, what does it mean? Like left-hand side, this picture. When the magnet is close to coil, okay, when it close to a coil, and inside the coil, the magnetic field increase to the left. Okay, so it doesn't want to change in the initial magnetic field, so it will repel the change. So it will induce the magnetic field rightward, like this picture. So if it induce a rightward magnetic field, and the current will goes down and goes into the left-hand side, this galvanometer, okay? And the right figure, when the magnet leaves, and inside the coil, the magnetic field decrease. Okay, it's decreased. So they don't want to be decreased. They don't want to change inside the coil. So it will produce a magnetic field to the left. It's like a compensation. Okay, so it will generate a magnetic field to the left, like this figure. So your magnetic field is to the left. So it will generate a current. Induced current go up and goes into galvanometer to the right hand side here. Okay, so this is a Lenz law. So now I have a magnet, and when it is close to the coil, and this coil connected with, okay, so when it is close to the bulb, and we can see the bulb will light up. And why does it light up? Because inside the coil, the magnetic field increased. So according to Lenz's law, and it will induce an opposite magnetic field, like this one, or like blue one. So we can see this will repel the magnets, because here is an N pole and this is an S pole. And according to the right-hand rule, if your induced magnetic field is to the left, and we should use the right-hand rule, we can understand the induced current is clockwise here. So it will slow down the magnet and produce the induced current. Okay, so now if the magnet is stationary and we can the bulb is dark, it won't light up because there is no change in inside the coil. So the magnetic field is not changing. So we can see the bulb is dark. Okay, so now if when this magnet leaves, okay, when it leaves, we can see the bulb light up again. So why does it light up? Because when you are leaving, you're inside the coil, the magnetic field decrease. So when it decreases, according to Lenz's law, they want to compensate it. So it will generate a magnetic field to the right, like this one. So here is S pole, so it will attract the magnet. So it will make the magnets slower. Okay, so according to the right hand rule, we can understand the induced current is counterclockwise here. Okay, so this is how we determine the direction of induced current. Okay, so let's make some conclusion about the Lenz's law. The magnetic field created by the induced current always opposes change in the inertial magnetic field. 那老师说过啊，就是我们回头看一下，其实这件事情呢，常常发生在你家里啊。为什么呢？比如说你跟你家人吵架假设对象是长辈，那当你过去跟他说，比如说爸爸妈妈，对不起，我错了，对不对？好，那他就会告诉你说，走开，我没有你这个儿子，是不是？好，就会叫你走开嘛。那当你无能为力，你真的要走的时候，他又跟你说，回来，站住，你给我回来，对不对？好，就是类似这种感觉，有点像我们说的这个冷式定律，所以同学可以去想象一下这样子。好，那接下来我们可能就是讲完这两个定律之后呢，我们接下来就要来讲一下应用喽。So let's see the applications about EM induction. The first application is a generator. So here is a simple structure. When we rotate the coil, and inside the coil, the magnetic field changed. So when it changed, and it will produce induced current like this one. So if I tell you the current is flowing counterclockwise, so can you tell me which direction the coil will rotate? Okay, I think it will rotate counterclockwise because when it rotates counterclockwise and the magnetic field increase to the right, and you will generate a magnetic field to the left and generate the current direction is like this one is a counterclockwise. Okay, you can imagine about that. And right hand side is a turbine. A turbine is hard to be rotated because it needs a lot of power. So usually we will heat the water to boil and become steam. And the steam will drive the turbine to rotate. So this is how we generate electrical power. So second application is transformer. Like every time we charge our cell phone, I believe everyone used this before. Okay, so it's not a charge line, it's called a transformer here. So the structure in the transformer, we have three parts. First one is a primary coil, and second one is a transformer core here, and the third one is a secondary coil. Okay, so remember that we use AC current here. 好，那它的工作原理基本上就很像之前我们在介绍那个电子感应一样。好，首先你有一个电流进去之后呢，你会怎样？你会产生这个磁场嘛？好，那主要线圈的磁场呢，它就会造成右边线圈的这个磁场的变化。那右边线圈就是二次线圈的磁场变化之后呢，它就会感应出感应电流。那但是它是怎么降压的呢？它是怎么降压的？我们可以知道首先它们的渣数不一样，所以你渣数 比如果是假设是220比10好了，哦，220比10，那就是会降1/22嘛，哦，就是会原本的电压会变成1/22倍。好，所以你家里都是110伏特啊，所以当你通110伏特的时候，这边就会降1/22倍。好，所以你一乘下去110乘以22，啊，你就得到5V 的电压。好，这个是它的工作原理啦。哦，好，那接下来我们继续往下看。好，那这边就是有一个影片啊，但是因为它在 YouTube，我没办法播了哦，因为这是要让它赚钱嘛，所以如果同学有兴趣，都可以用这个去看一下，好吧？好，那最后我们来看一个范例啊，那这个范例就是在翰林版的120页了哈。它告诉你说，这个手摇手电筒呢，不用电池就可以照明。那它的结构原理如右图所示。他问你说，从静止开始顺时针转1/4圈哦，那这好像是刚刚老师用双语讲解的问题嘛，对不对？那他问你说，这个磁力线的数目变化跟应电的会怎么样哈？那第一个，其实我们可以很明显的看到，这个本来的永久磁铁产生的磁场呢是相同的，所以当你今天顺时针旋转的时候，你线圈内的这个磁场会向左增加。那向左增加，根据冷氏定律，我们就不想要增加，所以我们就会向右嘛，对不对？好，那产生一个向右的磁场，哦，如图所示，紫色的这个箭头。那如果你产生一个向右的磁场的话，那就请你用安培右手定则去判断它的这个电流方向，哦。那这电流方向会变成是从乙流进来，再从甲流出去，哦，所以这题答案呢，我们就选 C 咯。磁力线数增加，然后应电流由甲端流出。好，我们今天的课程就到这边。